Okay. So the die size increase according to our results is 0.15%, which is very low for DRAM. Subarray address latches is the main cost, and designated bit latches and the wire, additional wire to control. There's also increase in storage cost in the memory controller that you mentioned, and that is in the paper. That's less of an issue because that's in the memory controller, because that's logic, pure logic. DRAM static energy increases because you activate a subarray and you lose static energy. But the hope is that the fact that you've activated many subarrays enables you to save dynamic energy because you're reducing the switching penalties. And we will see that in the results. And control, actually it's here basically. There's additional storage to keep track of the subarray status and keep track of new timing constraints. And you can read more about that in the paper. So we actually have cheaper mechanisms. We can go even cheaper. What we did was we eliminated all of these issues. But that was massa. You can actually get rid of these designated bit latches and enable just some level of parallelism without keeping many local row buffers activated. Then you get something like SALP2 that's described in paper. And you can actually get rid of these latches and tweak the architecture a little bit such that you can enable a little bit of parallelism. You can basically reduce the serialization a little bit, and that's SALP1. And I'll encourage you to read the paper. So you can actually build, there's a family of mechanisms in the paper. I've described you the most complicated one. The cheaper ones actually have some impact also. We'll take a look at that. This is the evaluation infrastructure. We have a bunch of cores, I think 1 to 8 cores maybe. There's a memory configuration. We varied the subarrays and looked at different ranks, banks, and channels. These are the mapping policies and DRAM controller configuration. You can read the paper for more detail. But the high level results, we have I think about maybe 50 workloads or so. You can read the paper again. These are the workloads that benefit most, and this is the IPC improvement across all workloads. Obviously not these, right? Otherwise you would tell me that this is a weird graph. It's not the mean, this is not the mean improvement of these values, obviously. But it's the mean improvement of all the workloads that we've studied for a single core. And this is massa. The improvement is about 17% in the single core studies. And if you look at the workloads that improve a lot, these are a lot of the streaming workloads. So you have a bunch of arrays that happen to map to the same bank. Now we're decoupling them and we can stream through those arrays. So if you're good spatial locality and you have multiple streams mapping to the same bank, we're decoupling them and we're getting a lot of performance. So actually this could be an interesting substrate for GPU workloads where you have lots of streaming and you have a lot of bandwidth need, but you have a lot of row buffer thrashing because streams happen to map to the same workload, same bank. So what is it compared to the ideal? The ideal here is if you eliminate all sharing between the subarrays and you enable 64 banks, for example, instead of enabling subarrays to be parallel. So the ideal buys you only a little bit more. So we get most of the benefit of the ideal at a very small fraction of the cost. And I'll show you the cost here actually. So these are the family of mechanisms, less costly, and this is massa, and this is ideal. If you look at the DRAM die area overhead, the ideal, if you replicate all of those decoders and enable independent banks, the DRAM die area overhead is, I would argue this is unacceptable, 36%. So if you have so this answers part of your question, I think. If you have 64 banks, this is what you would get, additional area overhead, 64 banks for each bank. And this is massa, and you can get cheaper mechanisms with some fraction of the cost. And this is still gray. Okay. What about the impact on dynamic energy? So this is the energy reduction. And the energy reduction comes from the improvement in row buffer hit rate. Now we're reducing the row buffer conflicts. Basically, this increases energy efficiency also. That's the key conclusion. And there are a lot more results in the paper, in both papers actually. If you're interested, have any questions, I'd be happy to answer after you look at the paper. So this is an exciting area, I think, going forward. How can you, now that you have these subarrays that are exported, that are exposed to the system, how can you exploit this in better ways is interesting also. Can you exploit this to do better mapping of data to different subarrays, for example? Can you exploit this to do better scheduling? Because now you have a scheduling problem at the subarray level. In this case, we did not do any intelligent scheduling. We used the existing row hit rate based scheduling, and we looked at some application-aware scheduling mechanisms that I'll talk about in the third lecture. And it seems to work well there, but I think there's potential there if you actually do better scheduling that's subarray aware.
Do you mean certain algorithms may be revisited to exploit rest of that structure, maybe?
I think so. I think for both ideas that I've described, you can devise better data mapping algorithms, request scheduling algorithms to exploit the structures much better. Okay, so we still have a little bit over time. But if you have any other questions on this, otherwise I'll talk about row clone a little bit and then we'll conclude. I can talk more, but I think people are getting tired. Okay, so this is another exciting thing I think that my student Vivek has developed. If you look at, and this is actually, I foreshadowed this a little bit. If you look at memory today, if you want to copy one page to another page, or if you want to initialize a page, what happens is pretty dramatic, I think, in terms of the latency, bandwidth, and energy. So what the processor needs to do is, or the DMA controller needs to do is, to access the source page byte by byte, copy it cache line by cache line, all the way to L1. And if you're doing it through DMA, all the way to memory controller. And then copy it byte by byte again, or cache line by cache line to the destination page. As a result, you get high latency. And this could be a 4 kilobyte page or 1 megabyte page, right? You also get high bandwidth utilization. You also get cache pollution, assuming you're bringing this stuff into the cache. And you get unwanted data movement, basically, all across the chip. You get congestion. So row clone, the key idea in row clone is to do this copy in memory. Basically, why don't we have a system where CPU says, here's the source page address, here's the destination page address, memory, do this for me. So we're going to try to build this. This is low latency, no bandwidth utilization. Well, low bandwidth, you still need to send the command. No cache pollution, assuming you don't need the data. You can be intelligent about it, of course. And no unwanted data movement in the system. So how can we do this? I've already given you the basic idea, actually. If you look at the DRAM operation, if you load 1 byte, you cannot actually operate DRAM in 1 byte granularity anywhere. So you need to activate this entire row. And that entire row activation brings the data into the row buffer, and you just mux out the data. So we're going to exploit this fact. And the mechanism is going to be very similar to the inter-segment migration that I've introduced earlier. So the idea of row clone is basically this. This is the source row. We activate the source row. And that brings the data into the row buffer. Now, once the data is stabilized in the row buffer, we're going to simply activate the destination row. And this will drive the data into the destination row. And if this is your page granularity, then you've done a page copy. And this is very fast, right? So the key idea is DRAM banks contain multiple rows of DRAM cells, and rows are on the granularity of 8 kilobytes today, if you actually do the have a rank, right? And a row buffer is shared by the DRAM rows. So you can do a large-scale copy by copying the data from the source row to the row buffer first, and then from the row buffer to the destination row next. That's the idea. It's very simple. Why does it work? I've already told you all of this, so I'm not sure if it makes sense to go over that again. Basically, DRAM row shares a word line. It's about this big. You have the sense amplifiers, and I think I've covered all of this. If you do an activate, what happens is this word line is raised, and the data gets copied here. And for a while, the data gets sensed, and after a while, you get the data here. And you don't know anything here. That's why you need to pre-charge the data later on. Well, after a while, actually, the data over here is stabilized, because now the sense amplifiers start driving the capacitors that were discharged. So you get both the data in the sense amplifier and the word line. Now, instead of pre-charging, when you do a pre-charge, what happens is this, right? Yes. So what we're going to do intra-subarray, if this is your source, this is your destination, we're going to first activate the source, and then deactivate the source. Actually, deactivate doesn't need to be visible to the memory controller, but internally, we're going to deactivate the source, and then we're going to activate the destination, which basically ensures that the sense amplifiers drive the destination lines, and you get the data that was in the source in the destination. That's the basic idea. So basically, the proposal is simply an activate that implicitly deactivates the source row. So today you cannot do this because that support is not there in DRAM. But this doesn't require any change to the DRAM core, actually. You just need to have a mechanism when you send an activate to one word line and then an activate to a destination word line, you deactivate the first one. And the sense amplifiers will drive the destination. That's the idea. So this works nicely if you're intra-subarray, right? Because within a subarray, you share these local bit lines. And you can easily transfer, and you share the local sense amplifiers. Now, if you want to do it between banks, it becomes a little bit harder, but you can still do it. Basically, you need to have a transfer command. The memory controller says transfer from source to destination. It knows where the data is, where the source is, and where the destination is. This way, the transfer is still done through the internal I/O bus in the DRAM. So you still don't expose the data to the memory controller, but it's not as fast. Basically, the transfer is pipelined. Basically, you read from the source and you write to the destination. If the data is inter-subarray, it turns out this is a little bit harder. What you need to do is you need to copy the source to a temporary row in some other bank, and then copy that temporary row to the destination. Because inter-subarray, you share the global drivers, and you cannot copy directly. Because you need to switch between read and write in that global driver, and you don't have those two ports. But you can read the paper. Basically, you transfer the source to the temporary destination, and then transfer from temporary destination to the real destination within a subarray, across subarrays within a bank. So the fastest part is certainly if the source and destination are within the same subarray. Okay, so you can use this mechanism for fast row initialization also. There are many cases in applications where you need to do row initialization. And basically you can fix a row at 0, for example. And once you do that, you can use the same mechanism, right? You can activate this. You can activate this one first, and you can activate the destination. Now you copied all zeros to the destination. You can imagine doing this making this more programmable. So for example, if you want to write all ones to a page, if you want to fill your memory with all ones, the software can populate one row with all ones and then do this, tell the hardware to do this copy across the entire memory. That's the idea. So I'm not going to give you full results because I haven't prepared the slides, but I'll give you just a teaser. You can read the paper for full results. Actually, we have an updated copy. But what is the latency and energy effects of a single page copy if you do this? This is the baseline. And baseline, if you look at the paper, it takes about 1,000 nanoseconds to do the page copy. We're going to reduce that by 11.5x. So it's a little bit over an order of magnitude, assuming that the source and destination are within the same subarray. And this leads to a reduction in energy of 74x for the 4 kilobyte page copy. It's assuming that, again, you remain within the same subarray. Now, if the copy is between two different banks, the latency reduction is smaller. It's about half. But the energy reduction is still significant. Now, if your source and destination are on the same bank but different subarrays, you actually increase the latency a little bit. You're better off going to the memory controller, it turns out. It's not that much. But the energy reduction is still significant. So where your pages are, source and destination pages are, determine the latency and energy benefits you would get with this support in DRAM. And the cost in terms of DRAM cost, if you look at the paper, I think the additional area cost is 0.005%. So it's very low just to ensure that you take into account that activate. Just so that you can support 2 activates in a row to different rows. And yeah, the paper has performance results also. There are many applications that do this copying. For example, virtual machines do a lot of copying, and networking applications do some copying. Actually, one of the difficulties with this evaluation is people try to avoid page copies like the plague. Because it is so costly, they want to redesign the software so that they don't do page copies. So I think this kind of mechanisms will enable new ways of designing software also, which is hard to evaluate, of course, in a single paper. But going forward, I think doing this kind of optimizations in DRAM can enable new software designs as well. People can be more interested in copying data at large scale. So actually, one application that needs something like that we're looking at is, I've already talked about heterogeneity, but you could consider memory as part of an accelerator also, right? In this massively heterogeneous system, memory is a heterogeneous component also. So you can have the specialized compute capability in memory. And row copy is one way of starting, I think, this specialized compute capability. The key is it needs to be low cost. So we're looking at enabling something called ultra-efficient visual search. So it doesn't have to be visual, that's why it's in parentheses. But let's say you have very large capacity memory and you have a database of something, for example, images, and you actually want to do a search. This is a tough problem today because you can have an image, and if you want to figure out what in your experience that image looks like, you need to do an expensive search. And the algorithms are not sophisticated enough to actually figure out exactly what that image maps to. So one solution to the problem is to do more or less brute force search. You store a lot of your images into your huge main memory, perhaps with storage class memory, and send the query from the processor saying that I'm searching for this image. And you can actually hash that image to a bit vector, for example. And basically the memory can compare that image to all of the images that it itself has in it and return the results saying that these are the images that match. So this is what we would like to enable, and this fast row copy is one step towards it, I think, that memory can do that copying inside. Now the key question is, can memory do other things that's required for this, and how efficiently can it do that? I think the key thing is really the cost, but there are several questions that are interesting to examine. What is the right partitioning of computation capability between these two different components? What is the right low-cost memory substrate? And I think the key is really low cost here. Otherwise, people have proposed some things like this, right? In the old times, 20 years ago, maybe 30 years ago, they proposed adding significant amount of logic in DRAM. And that's even when DRAM doesn't scale, I think that's going to be a very tough proposition to make happen. But figuring out ways of taking advantage of the internal structure of DRAM is potentially a different way. What memory technologies are the best enablers is an interesting question, and we'll talk about memory technologies in the next lecture. Maybe DRAM is not the best enabler, but maybe there's some other technology that can enable this search more efficiently. And then the last question is, I think, how do we rethink and ease the search algorithms and applications? Of course, something like this requires a lot of cooperation between the algorithms and people who have graphics expertise like K1 and also architectures. So I think I see row clone as a first step in enabling something like this. Okay, I guess I'll briefly cover some ongoing. Any questions, by the way? Yes.
Is this kind of extension of the small content addressable memories for fast table search? You're extending this idea to the DRAM in a way? So
we don't want to build a content addressable memory. I think I know what you have in mind. Something like a TCAM, for example. So we don't want to build a huge content addressable memory that's going to be very high cost. But we want to do large-scale operations. For example, row clone does a large-scale copy. Can we do large-scale XORs or large-scale compares?
I first thought this was a kind of hardware support for relocation in DRAM. But I understand this is not just a relocation. You're simply copying, making clones of
That's right.
rows. So you can better do parallel search kind of. Is that right?
That's right, exactly.
Inject computation into the memory and do parallel search.
That's right, yes.
Okay.
And it can any place where copy or initialization is used, that could be useful as well. But we need some more things for search. Okay. Yeah, I'm not sure if I'll go into any of this. Actually, I have a lot more to talk about, but it's probably a good time to end. But we're looking at online retention time profiling, as I discussed. You can actually parallelize refreshes and demands in more scale. Certainly more computation in memory and controllers, and efficient use of 3D stacked memory that we didn't talk about today. I actually have a couple of other readings. Like one is memory voltage and frequency scaling, which I will not talk about, but you can read that.
Those you don't have time to discuss here. Do you put those slides in later?
Yes, the memory voltage frequency scaling. I will put those over here. These I don't have slides for, so I won't be able to put these, but I'll put those slides that I have available as part of the remaining part of the presentation. Looks like we're already at 230 slides, so PowerPoint may crash a lot. Okay, so I think I'll conclude this part of the lecture. Basically, main memory scaling problems are, I think, a critical bottleneck for performance, efficiency, and even usability going forward. There are two solutions. I did not discuss this part. One is tolerating DRAM with novel architectures, and I think I've skipped a couple of things here, but you can add SALP here, subarray level parallelism. One problem was refresh. Retention-aware intelligent DRAM refresh is interesting. That reduces the refresh operation significantly. The second one is how do you reduce the latency of DRAM without losing capacity? And I think tiered latency DRAM provides a nice substrate for those optimizations. Subarray level parallelism enables more parallelism in DRAM and also enables new opportunities, I think, that we've discussed. And row clone also enables very fast page copy and initialization mechanism that could change how you design applications. And that could also change the applications today. So actually, the paper, the revised version of the paper has extensive evaluations with things like fork and checkpointing. You can increase the checkpointing where you copy. So a lot of systems for reliability purposes checkpoint the architectural state of memory periodically, especially large scientific systems, right? And that checkpointing speed can be improved significantly if you do this checkpointing, if you have an area of memory that's actually where you can copy data really fast into. There's also, I guess we also discussed self-optimizing memory controllers, and I think that's an interesting direction. Maybe it's not exactly to tolerate DRAM, but it may be to tolerate the complexity of DRAM as we go forward. And I'll talk about this tomorrow. Basically, we'll talk about how to replace DRAM with non-volatile memory chips by architecting these non-volatile memory chips well, and how to design hybrid memory systems with automatic data management. And I think going forward, software, hardware, and device cooperation is essential for effective scaling of main memory. It's going to be very tough to scale memory just with circuit level and device level solutions. You will need to expose, for example, I see a radar as exposing, a device exposing its characteristics to the higher parts of the system such that you can do something about it rather than trying to fix the problem in the device level. Okay. Okay, I guess that's a replicated slide.
As you mentioned, this may be used to enhance the reliability. Instead of correcting more bit errors to put devices like that, you may just put detection. And if you have a row clone, then if you detect something wrong, then you may access the clone, and hopefully this will not be hit by that software kind of thing.
That's right, exactly.
You need row copy in such cases.
That's right. That way you actually, if you do fast row copies, that you can enable something like that better. Okay, that's all I have today. I'll see you tomorrow.